Right, I make it 5 past, so this is as good a time as any to start this session. Thank you everyone for coming to this second session, the second of 3 sessions given by Archer 2 and by us at EPCC to teach people what I consider to be the basics of, or at least the basics of what you need to run LAMP simulations, and specifically to run LAMP simulations on Archer. Like last week, like last week, the idea of this is I'll be talking through a couple of things. If you have any questions, please post them in the chat. I'll read them out and answer them as I see them. I'm not too sure whether this will be an hour, like an hour-long first part with a half-hour break and then an hour-long second part, because some of the stuff that I was going to cover this week, I ended up covering last week, which is why we overran by a bit last week. My apologies again. So I'll see where we are when I feel I've hit the halfway point in the slides, and I'll ask you whether you'd rather just carry on from that point to finish, or whether you'd rather have a break. That seems like the best way to do this. Again, I want to emphasize that all of the information for this course is available on the course Git page, which is accessible from the Archer 2 training website, I think. And today we're going to be covering things from day 2. So everything I'm going to talk about and every file that I'll be using, you can find in the day 2 directory. I've also been working on the exercises. They're not fully complete. I've got all of the exercises and all the exercises that we'll be doing like set up, and I have all of the input files. I've just not written the questions yet. So I'll be writing those over this week, but there's already a couple that are ready. Definitely the performance tests are ready, and I'll be finishing the water evaporations after giving this lecture. So feel free to have a play around with those if you want between now and next week, or feel free, you should have time to do most, if not all of them, next week during the exercises class. So with all of that done, let's get to the actual lecture. So this week we'll be delving deeper into LAMPS. Just like last week, you are more than welcome to reuse this material. You're welcome to share it with whomever you want. The video from last week's lecture is already up on YouTube. You can also, the video from this lecture will also be up on YouTube. You're welcome to share the videos, the slides, whatever, with whomever you want it, provided that you make sure to, A, not sell these things on, don't profit from it, because after all, this is my work and the work of other people who helped me in making this. And B, ask them also not to share, or ask them also not to sell the contents of these slides. Also, much like last week, most of the things I'll be talking about today can all be found in the LAMMPS user manual, which is a very, very good manual, probably one of the best for molecular dynamics packages that I've had to use. So with that, what's the overview for today's course? Well, first of all, I'm going to go over very briefly the exercise problem that I set at the end of last week and go over the solution to that problem. Then I'm going to talk a bit about domain decomposition. And domain decomposition is, well, actually, whilst talking about that, I'll touch on the wider topic of how do you run simulations efficiently when you're using more than one processor. How can you judge how many processors you should run, and how do you make sure that all of the processors you're using are, you know, doing the work you want them to, so that you don't have one processor doing nothing and one processor doing all the work. After which, we'll talk briefly about compiling LAMMPS on Archer, and I'll show you how you can compile LAMMPS on Archer. There's some quirks to compiling on Archer, but overall it's going to be incredibly similar to if you were to compile LAMMPS or were to try to compile LAMMPS on your system, at home, on your laptop, even at work. And then that's possibly the point where we'll have a short break, maybe not. And after that, I'll talk about altering LAMMPS source codes and actually show you some of the LAMMPS code, how you can change it, how you can move around in LAMMPS directories, what you can do to speed things up, what you can do if LAMMPS doesn't have one of the functionality that you're after, what can you do to try to add it. Before the break and before the end of the session, I will make sure to answer all questions that have been asked up to that point. And as I said, if I spot your questions as I go, I will answer them as I go. So with that, let's start with last week's question. Last week I asked, or last week at the end of the session, I gave you all an input script, and I mentioned, or I asked you guys to, if you had time and if you were interested, run those simulations at 3 densities, whereas all of the work we showed last week was run at a density 0.6. I asked you guys, well, how about you run a simulation at a density of 0.05, 0.8, and 1.4, and specifically look at the radial distribution functions, the RDFs, that are output from those simulations, and have a look at how they differ. So why did I choose those 3 densities? Well, actually, the answer is quite simple. The logic behind the choice of these 3 densities is that at 0.03, at 0.05, your system is in a gaseous state. If you look at, this is the simulation box. The simulation boxes are not to size, as you can tell. The atoms, or sorry, the simulation box on the left is not the same size as the simulation box on the right, but all the atoms have the same diameter, so that gives you an idea of how much bigger the simulation box on the left is compared to the one in the middle and the one on the right. And each simulation box has the same number of atoms. The simulation box on the left is in a gaseous state. There's no real clusters of particles. You've got sometimes pairs, maybe triplets hanging around in places, but overall, it's relatively evenly distributed, and it's a gas at that density. Whereas the one in the middle is definitely not a gas in the sense of everything is clustered together, but there's no crystalline structure to these clusters. So it's kind of between a gas and a solid. So guess what? It's a liquid. That's, yep. The middle one is a liquid, and the one to the right, you can start to see some structure. Well, you can see some structure. You can see that all of the particles are sort of in lines. So like these 3 here are in a line, those 3 here are in a line, the 3 behind there are in a line. They're all in sort of the same structure. And at a density of 1.4, yeah, the reason they're in structure is because it's a solid. And the thing I wanted to really emphasize is the difference in the radial distribution functions for those 3 functions, for those 3 states. This is there's 2 reasons why I wanted you guys to look at this. The first one is this problem of, can you get a Lennard-Jones fluid to go from a gas to a liquid to a solid, is one of the first problems that was looked at using molecular dynamics. So, just for the historical significance, I thought that would be fun. The second one is because it's also a very visual problem. Like, you can tell definitely that from the simulation boxes that one of them's a gas, one of them's a liquid, and you can probably tell that the other one's a solid. But also you can then look at the radial distribution functions, which are functions that compare the fluctuations in atom densities at a radius around an average atom, compared to if the density was fully, compared to if everything was perfectly uniformly dense. So if you have a perfectly uniformly dense system, your radial distribution function would just be a flat line at 1. But because there's local fluctuations, especially closer to to each particle, it's not. That's very rarely the case, if ever. So for the first system, the gas system, you've got up until a radius of roughly 1, which is roughly 1 diameter, unless you've got two particles that are roughly 1 diameter away from one another, there is absolutely no particles, which makes sense because essentially each atom excludes every other atom up to a distance of 1 atom diameter away. And as soon as you hit that, there's a peak, which exponentially dies off. This is a signature radial distribution function for a gas. For a liquid, you get the peak at roughly the same point, but instead of exponentially dying off to 1, like it did in the gas, you get fluctuations about 1 that slowly die off. That, again, is a signature radial distribution for a liquid. If you see that sort of radial distribution function, you've got a liquid. And then the final one is possibly, well, I mean, the one that I find most interesting in terms of radial distribution functions is for a solid. If you have a very high peak, so in comparison to the peak that you get in the gas or the liquid, this peak in the radial distribution function hits all the way up to 5 as opposed to 2.53-ish. You get a very high peak that's very, very narrow, and then you get further peaks that follow a set pattern, but also tend towards 1 eventually. If you go far enough away from if you go far enough out with the radial distribution functions, you should always tend to 1 unless you've got a perfectly crystalline structure. So that's the answer to the exercise last week. I find it interesting. I hope you guys do too. So next, let's start talking a bit about running molecular dynamics, and specifically running molecular dynamics on large systems. The easiest way to talk about that is to start with domain decomposition. So imagine that you're running your simulation on a single core. You have a simulation box. It has 1,000 particles, exactly like we had last week. It has 1,000 particles, and for each of those particles, you're running molecular dynamics, which means that at every time step, you've got all of the particle positions and their velocities. You assume that they'll carry on at a constant velocity for your small time step delta t. They reach their new velocity. They reach a new position after delta t. From those new positions, you work out the new energy acting on every particle. From that energy, you work out the force acting on every particle. And from that force, you work out the new velocity, meaning that you are back to a state where you have the new positions and the new velocities for every particle, and you can keep repeating that and repeating that and repeating that. On a single processor, on a single core, I use those words interchangeably, just to warn you. On a single processor, it's clear that all of the work, every single calculation for every single one of those 1,000 particles for the entire simulation will be carried out by that one processor, because there's no other processor doing anything. Now imagine that you're using more than one processor. Imagine that you're using 4 processors, this is the example I've chosen here. Then what happens? In LAMMPS, naive, unless you tell it to do anything else, if you are running LAMMPS with more than one processor, LAMMPS will say, okay, you have a simulation box. I will try to split the simulation box as evenly as possible spatially. Meaning that if you've got in this case, the simulation box is a perfect cube. If you have a perfect cube, LAMMPS will just split the cube in 2 directions so that you've got 4 sections. One rectangular prism here, 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 and here. Obviously, you can't see the Z direction, but believe me, there is a Z direction in this. So it splits the box into 4 rectangular prisms of exactly the same volume, and says, okay, processor 1, you deal with all of the particles on in prism 1. So let's say the top left corner prism. Processor 2, you deal with top right corner. Processor 3, you deal with bottom right corner. Processor 4, you deal with bottom left corner. And each processor will then calculate all of the energies, forces, velocities for all of the particles within those that prism, and will then move all of those particles to where they need to be. Now, for a particle which is dead in the center of that prism, that's absolutely fine, because because essentially all of the particles that interact with it, all of the particles within the neighbor list cutoff and within the Lennard-Jones cutoff that we had before, all of those particles are on the same processor. So all the processor already has all of the information for those, and it just happily works out what's happening there. However, imagine that instead of a particle smack bang in the middle, we're looking at a particle, say this particle here, which is right on the boundary. Well, a couple of things start to occur. For one, half of this particle's neighbors are on another processor. For two, it's also possible that this particle might end up having a downward force, or the particle on the edge might have a force that leads it to pass that edge into the domain of another processor. So how do you get around that? Well, the way you get around that is by communicating. The processors will update each other to say, oh, I've got a particle near the box. I need information for this neighbor, this neighbor, this neighbor, this neighbor. Can you send it over to me? And the next processor goes, sure thing, here's the information. Or also it can go, oh, this particle is about to pop over the box. Here's all the information for this particle. Good luck. And the other processor says, thanks, and starts dealing with it. So that's how domain decomposition works, very, very crudely. Well, part of the thing with that, as I said, is for particles around the edge, you need communication. And that communication takes processing power, meaning that when processors need to communicate, that costs something in work, but also that costs something in time. Let's say processor A has finished all of his calculations for all of the particles in his processors and now just needs to deal with the certain, with a couple of particles on the edges of its domain. But processor B is nowhere near finished. Processor A is going to be sat there waiting for processor B to eventually pass it the information it needs over so that it can completely finish its update. That's another place where you can gain. That's another place where communication can be expensive just by having idle processors sitting around doing nothing. Now, one of the nice things about LAMMPS is that all of this information is actually nicely output in the log file. So I'm just going to copy over from yesterday, copy over from last week, the log file to this directory. And let's have a look at the log file. The log file, we've looked at it before. First of all, it gives you all of the information from the simulation we've run, including what sort of pair styles you're using, including here at the very top, how the box is split between processors. So you'll notice that it says we've got a box which is 0 to 11.8 particle width long in 3 dimensions. It tells us here that we're running on 24 processors, so the box will be split into a 2 by 3 by 4 region, each of equal size, or each of equal volume. And then it tells us all of the stuff we've output before getting to what's been output to screen during the simulation. And then eventually, at the very end of the simulation, it gives us all of this really great information, starting with the loop time. So the loop time, first of all, tells us how long the simulation took to run. In this case, 5 seconds on 24 processors for 50,000 steps with 1,000 atoms. That's loads of information. Then it tells you performance information. So if you were going to run this for an entire day, how long, how far into the simulation could you get? How many time steps per second are you doing? How efficiently were your CPUs used? Now were your CPUs used? Now we're starting to get to the information that gets interesting. And here, the NPI task breakdown tells you a whole lot of information, like all of this bit. It tells you the average time spent, the maximum time spent, and the minimum time spent per processor, or for the processors, on the pair style, on calculating pair styles, i.e. on calculating the Lennard-Jones interactions between between sets of pairs of particles, for the entire run. It tells you how much time was spent building up neighbor lists, how much time was spent communicating between processors, i.e. how often did the processors have to say, hey, you've got information I need, or hey, here's the information you need. How much time was spent writing the output, i.e. writing all of the stuff here, and any dump files and things like that. The modifies is how much time was spent caring and working out fixes and computes, both of which I talked about last week. And the other time is time spent not in things that I've already talked about. And here we notice something very, you'll notice very nicely that we had a 1,000 atom system on 24 cores, which means that, roughly speaking, that's 40 atoms per processor, if I can still do maths. I think that's about right. So 1,000 atoms on 24 processors, which means that on average, each processor only has 24 atoms to deal with. And 24 atoms is not masses of atoms, which means that most of them will actually be on the edge. So the processors will need to spend a lot of time communicating between one another. And as expected, the communication line, if you look at the final column, which is the percent of total time spent on this step, a whopping 42% of the time it took to run the simulation was spent waiting for the processors to talk to one another. This isn't surprising. 24 processors for 1,000 atoms is massive, massive overkill. But on Archer, when running simulations, you always ask for integer numbers of full nodes. So you always have to ask for 1 or 2 or 3 nodes. You can't ask for half a node at any point. And each node has 24 processors. So the reason I've been using all 24 processors on this system, which is really just to show you guys how it works, by the way, the only reason I've been using the full 24 processors here is because if I only use 12 processors, well, we might gain in communication, while the other 12 processors would be sat around doing nothing. So I might as well use them. Usually I would run much larger systems on this set of processors, but actually this is going to be one of the exercises. This idea of how the number of particles can affect the communication time and can affect the runtime of simulations is one of the exercises for next week. So yeah, something to look forward to. Right, back to the slides. But just to emphasize while I swap over, LAMMPS does provide a ton of information. It's always worth checking out your log file if you feel that things are taking too long or things aren't running quite the way you want them to. Look at the log file because it has very nicely broken down information, and that's always the first step for to speed up your simulation. So we've got a system. In our case, by the way, in the case that I've just shown, sorry, I've got a question. The question is, why did I not choose 12 cores? So I could have chosen 12 cores if I'd wanted to, but I ran this system on Archer. And on Archer, when you submit a job, you ask not for a number of cores, but for a number of nodes. And each node has 24 cores. So I asked for a single node, and then I have the option of attributing as many cores as I want to that job. So I could have used 12 cores from the 24 that I've got, 13, 14, 15, up to 24, and down to 1 if I'd wanted. The reason I chose 24 is a twofold reason. The first one is, while there's an increase in communication cost, I'm aware that the simulations still run faster at 24 cores than they would at 12. And secondly, the other reasoning behind it is even if I only did 12 cores, I'm still paying for 24 cores, so I'm only using half of what I'm paying for. But either way, this simulation is not a good use of resources. I hope that answers the question. Cool. So, in this case, as I said, this is not a good use of resources, but there are certain cases where the idea of just splitting up your system into chunks of equal size is not a good idea. For instance, let's imagine for a second that we have a system which has all of the particles in the bottom half of the box, and in the other half of the box is entirely empty. The top half of the box is entirely empty. If you split that into equal chunks, half of your processors are going to have a ton of particles, half of your processors are going to have no particles, meaning that the half with no particles will be sitting there doing nothing, while the other half of your processors, they'll be working way, way more than they might need to, or could, because they've got way more particles to deal with than just the average number of particles per processor. So with those sorts of systems, you'll probably want to decompose your domain, i.e. split up your simulation box between processors in smarter, more efficient ways. LAMMPS has a couple of ways of doing that. And the way you do that, roughly speaking, is by using the balance command. This picture at the top, or these three pictures at the top, are just taken straight out of the LAMMPS manual, by the way. And it really exemplifies, imagine you've got a box which is not uniformly dense. So you've got particles at the left and bottom edge, but no particles in the top or right. Well, in that case, if you just split your simulation box without any commands, LAMMPS will naively just cut your box into 16 chunks for a 16 processor job, with some processors having loads of particles, some processors having no particles, meaning, as I said, some processors will do no work at all. LAMMPS gives you the option, there are two main options, but LAMMPS gives you the option of rebalancing the number of particles per processor. Those options fall into either the grid type of option or the tiling type of option. The idea of the grid type of option is you still try to keep a grid-like structure, and you try to make sure that each processor ends up with a like the domains might be of different volumes, but the start and end position of each domain is still linear. So you end up with these lovely lines down the center of the simulation box. It's just that certain sides of the box are bigger than other sides. So here in this case, this simulation box, using the grid type, the bottom left simulation part of the simulation is much smaller than the top right part of the simulation. However, you'll also notice that for this very specific example, this grid type command still leaves some imbalances between the processors. So the top right processor has no particles, whereas the top left processor seems like it has possibly the highest number of particles in that simulation. But in a lot of cases, the grid type command works very well. Another option you have is to use the tiling command. And the way the tiling command works is, instead of having a lovely grid-like structure, LAMMPS will go, okay, we need to split this so that each processor has roughly the same number of particles, more or less. So let's start splitting, and it'll go around trying to make boxes that that contain the same number of particles, give or take a few. So again, in this example, I would say that this simulation box actually probably does have roughly the same number as this simulation box, though it's hard to tell just visually. So every processor ends up with the same number of particles, or roughly the same number of particles for which to compute all of the steps. But in calculating this, there is a cost. Instead of just saying, okay, I'm going to cut my simulation box at x equals 1, then x equals 3, then x equals 7, Here you've got to say, okay, I'm going to cut my simulation box, and this chunk's going to go here because this equation says so. The equations are a bit harder. The equations take a bit more computational time. There's a slightly added cost. So choosing which tiling method to use can be tricky. So once you've chosen whether you want to go for a grid type method, which in LAMMPS is using the shift balance command, or a tiling type method, which in LAMMPS is using the RCB balance command, you can then choose, there's one of two ways to rebalance your system across processors. The first one is you can have a command called balance. And what that does is when LAMMPS first reads the balance, it'll say, okay, I need to rebalance the particle positions between the processors. It does it once, and then it keeps going, and processors keep the particles that they were attributed at the start. It never bothers with it again. The other one you can choose is the fix balance command, and that one allows you to give a criterion. You get to say, well, when the imbalance between processors is more than 5%, i.e. when processor 1 has, or the processor with the most atoms has more than 105% of the processor with the least number of atoms in it, that's when I want you to rebalance everything again so that everything gets roughly the same numbers. Again, balance, very low cost in comparison to the fixed balance, but fixed balance means you might be able to save time down the line because all of your processors are working more efficiently. So there's always off, and it's always a bit tricky to try to decide which to use, if any. I think I've already described the two types of domains. The last thing I wanted to mention is if you want to use the tiling type, by default, LAMMPS will assume that you want a grid type and a normal grid type without any balancing. If you want to set specifically the tiling type, you will need to set as well a variable called comstyle in order to make sure that LAMMPS knows to use the communication style for tiling, for tiled decomposition as opposed to grid decomposition. Why is that important? Well, in grid decomposition, each processor, let's say the processor with the white domain in like second from to the right, second from the top, that processor knows that always its top neighbor will be the box above it, its bottom neighbor will be the box below it, and its left neighbor will be the box to the left, its right neighbor the box to the right. However, with the tiling command, you can end up in situations where, say, the purple subdomain in the tiling picture, the one that I'm circling now, I don't know if you can see my mouse. I think you can. But yeah, the purple subdomain here, well, at the moment, it doesn't have, at the moment, it's got these four neighbors. At the moment, it's got these four neighbors, these four neighboring processors, but when you retile everything, the neighboring processors might change. So you need to keep also track of which processors are your neighbors. Again, it might still all be worth it if the amount of time you gain by making sure that all of your processors are working as efficiently as possible is greater than the cost and time you have to put in to redistribute everything, it's still worth doing. And again, as a teaser for next week, there is an extra problem which is looking at balance and changing the processor balance or the processor domain decomposition in order to get the most efficient simulation runtime for a simple simulation. And the results are, I find them interesting, but roughly speaking, by adding a balance command for that simulation, you're able to increase your computational speed by threefold or something like that. So if you learn more about that, or if you have any questions about it, next week will be a great time to talk about it, and I'll happily talk about this sort of thing for way longer than I probably should. So with that, let's move from domain decomposition. Are there any questions about this so far, by the way? Just a quick check. It looks like no. So keeping going, let's move on to compiling LAMMPS. As I mentioned last week, Archer has a modular system, and one of the modules is LAMMPS. There is a pre-packaged version of LAMMPS that is compiled and kept and maintained by EPCC, by us, that users can use. However, sometimes some users will want certain libraries that we've not installed, or will want their own version of LAMMPS that has things that don't come with just LAMMPS off the shelf. And in those cases, you might need to compile LAMMPS. So here I just wanted to run you very quickly through how to compile LAMMPS. I'm probably not going to compile it live because it takes about 10 to 15 minutes of staring at a screen, staring at a shell script doing not very much exciting, but I'll show you the steps at least. Or maybe what we'll do is after I've set everything up in such a way that it can compile, we'll compile it during a break. All of the instructions that I will be running are on this page. This page you can get both from the GitLab page, or sorry, these slides you can get from the GitLab page, and you can also get it from on Archer itself. Let me swap back to shell. So all of the material that I'm covering today and everything that I'm using today, you can find in the directory /work/y14/shared/LAMMPS workshop day 2 material. Everything that I'll be showing today is in that directory as well. So if you're on Archer and wanting to do these as I go along, you're welcome to. I will post the, sorry, one moment. I will post this in the chat. I don't know how many people are following along, but that gives you the opportunity to if you want. And the first step to this is quite literally to copy the, to clone the LAMMPS directory from Git. So git clone, you want to choose a stable branch. If you don't specify that you want the stable branch, you might end up with whatever the latest version is, which might or might not be entirely stable. Unless you're doing anything fancy or anything that LAMMPS developers are currently playing with and currently obviously playing with, the other branches should be fine as well. And you want to plonk everything into a directory. In this case, I am cloning everything into a directory called LAMMPS2. Everything will download, and that'll take some time. And because I'm not happy about waiting for these things, I've actually already copied them across in a directory called LAMMPS. So once you've downloaded everything from the Git page, you have everything you need to make LAMMPS. There's a README, which from memory has information about who owns LAMMPS and where you can find information, including where you can find the manual. Again, the Holy LAMMPS manual that I keep referring to, it's really, really good. You also have a number of different directories. There's directories for benchmarks. There's a CMake directory for if you want to use CMake to make it. I'll show you how you can do that in a sec. Docs is the LAMMPS manual, but you can build your own manual here. Examples is a series of really, really good examples, which I'll talk more about after I've shown you how to compile this. Lib is libraries for if you want to have certain special features added to LAMMPS. Potentials, Python for if you want to do work on Python. I cannot remember what's in potentials. I don't think I've ever had to use it, but it's got different potential files for if you ever want to use those. So handy. And SRC and tools. SRC is the source file, and that is where you want to be if you want to install LAMMPS. If you are running this from your home laptop, or if you're running this from your home desktop, your work laptop, and if you're running some version of Linux, usually you should be able to just make LAMMPS from here without doing anything by doing no more than typing make open npi. It's not going to work on Archer because Archer is a bit weird, but that's 8 times out of 10, I'd say, on a Linux system. That's all you need to do. On Archer, however, we've got, as I said, modular systems, and LAMMPS prefers Intel compilers. So we've got to set up a couple of things. First of all, we need to switch from the current programming in. Oh, there's already in Intel. Oh, that's because that's from 4. Sorry. 1 second, just to make sure that everything is clean and as it should be. Let's restart that. Apologies for that slight delay. Because you want things to be done in Intel, the first thing you need to do is swap the programming environment from the default switch as well. Swap the programming environment from the default Cray to the Intel environment. That's step 1. Step 2 is we want to swap to make sure that we've got one of the latest versions of Intel compilers. And actually, if you double tap, it autocompletes and tells you everything that's available. We want the 17.0.3.191 because it's, I think, the most recent. So I'm not sure. I'll look at it. Then we also want to make sure definitely that we've got the latest version of the GCC, the GNU C library. At the moment, we've got 4.8.1, but actually there's 6.3.0 installed, which is much more up to date. And actually, on Archer, LAMMPS will not compile with GCC 4.8.1. You need 6.3 to get it to run. So do make sure you've done that. And last but not least, we want the fast Fourier transpose module because it things up. Once we've got all of this, so we've got all of our modules, which you can always see what you've got by doing module list. That shows you all of the modules that you've got currently loaded up. So you can see there's the Intel that I just loaded up. There's the fast Fourier transform that I just loaded up. There will be GCC 6.3 is here. And FFT, this is in alphabetical order. I cannot find it, but it's, there it is. It's right at the end. It's not in alphabetical order, clearly. So everything that I've loaded up is now available. The next thing you do is in the main LAMMPS directory, there's 2 ways you can build LAMMPS. You can either build LAMMPS let's try that then from my home system. sorry about that, everyone. And second apology, I will unfortunately need to now download LAMMPS from Git. But yeah, actually, that's probably the best time that that could have happened, because essentially everything that's Archer dependent, I'd sort of already talked about. And now we can try if the MPI thing actually works. So while that's downloading, are there any questions? No questions? Sorry about that, by the way. From the looks of it, that's a unexpected issue with Archer, which is why the system just went down. This is, I think, the first time that that's ever happened to me. Definitely the first time that's ever happened to me during a course. So my apologies for this slight hiccup. Let me check real quick whether actually. Is the process for compilation on Archer and Archer 2 the same? Is a question I've just received. It will probably be slightly different. I can't go into much more details than that, but I imagine it will be different. And when it is, when we're more aware of the like when we know how to compile LAMMPS sensibly on Archer 2, I will be updating the slides for this course so that they're up to date for Archer 2. How is it different for other supercomputers? Well, other supercomputers will have different modules set up, so there's always the trick of trying to find which modules are the right ones to use. But overall, you'd expect that provided you've got Intel modules, Intel 17-ish, and GCC 6.3-ish, everything should be the same. It's just a case of linking to the libraries, to the correct libraries. I hope that answers that question. What I've not answered definitely is how do you link to libraries for certain, or how do you link to libraries on other supercomputers? And the reason I did not answer that is because that varies from supercomputer to supercomputer, and indeed from personal computer to personal computer. Right, this is taking too long. I can't be bothered to wait. So I've got a pre-downloaded version from a while ago. So let's use that instead. Again, my apology hiccup. So we find ourselves on my laptop instead of Archer with a version of LAMMPS that I compiled previously. At this point, to make LAMMPS, you've got two ways that you can make it. You can either use make or CMake. If you want to make, the way you make it is you type make open MPI. Do not type make MPI. There we go. You make MPI. And because I've previously installed it, it's telling me, well, you've already got the version that's up to date. Why do you want me to make this? If I make clean all and then make MPI, now it's starting to do the compilation process. And the way that it does this is it will start going through a certain number of makefiles, in this case, the makefile.mpi, and having found my local system's MPI library, my local system's C++ library, my local system's other libraries that it needs, it just happily starts compiling all of the C++ files here. What files is it making? Well, basically, if you're in the source directory, it will make all of the files that are currently found in the source directory. So everything directly here will get compiled and will get added to LAMMPS. This is an important thing to bear in mind if you're wanting to later hack your version of LAMMPS. Sorry. But at the moment, the files I've got start with accelerator.cocos.h and will go all the way to whatever Z was. There are certain directories, here they come up in blue. The things in those directories are further files that you can add to here if you want to add certain functionalities to LAMMPS. So for example, the first directory we get is asphere, which is the which will have all of the files that you need for running aspherical particles or systems of aspherical particles. So things like the gay burn potential and things like that. Claire has just posted, I'm sure you've all read this faster than me, but for anyone on Archer just now, there's a system issue and the machine is presently unavailable. Apologies for any inconvenience, and our team is busy looking into the issue. Great. So every C++ and header file in here will be compiled and combined to make the Archer executable. Everything not in the C++ or header files, i.e. everything that's in a directory, will not be included. Sorry, I'm going to have to zoom all the way down with this. There it is. So apparently not Z, but write restart is the final one. So if we look now at the aspherical directory, you'll notice that there's a bunch of new C++ and headers which are not currently here, are currently in the top directory. Or they are because I've compiled this with aspherical. Let's try a different one, Voronoi. I've definitely not done Voronoi. Hope I've not done this. This would be a terrible example. Sorry. Here you go. So Voronoi, I've never compiled with Voronoi, so it does not find this file compute Voronoi atom, which is in the Voronoi directory, but is not in the src directory. Yes, I'm aware that for Voronoi I'll need certain files, and it's not one of the packages that I'll be showing you things with because I need to install libraries, but I'll talk about that in a sec as well. So how do I know what's already been made? You can use the make package status command, and that will list every package that LAMMPS has, starting with aspherical, which is installed, and going all the way to the user packages, which I'll talk more about in a second, and including Voronoi. And you'll notice that next to Voronoi it says installed no, meaning that Voronoi is not already a part of this specific version of Archer, LAMMPS. And if I wanted to install it, I could do certain steps towards it. For the case of this example, I'll be using the granular, the files in the granular package, because I'm aware that I don't need to install libraries. It's a relatively easy one to install, and it's currently not installed on the version of LAMMPS. So ls granular, as you can see, there's a bunch of C++ and header files here, and if I copy one across, that's not currently in the source directory. There are two ways that I can go about trying to install a version of LAMMPS that has all of the granular packages. I can either do make yes granular, which will copy everything from the granular directory into the source directory. So if I now do ls fix freeze, it's now present. This is one of the easiest ways to get rid of packages as well. All I need to do is make no granular, and now that's no longer in this source directory. The other way I can do it is by hand. So copy everything from granular into the source tree, and now first of all you'll notice. Let me back up a second. So I've uninstalled the granular directory. If I do make package status to show the status of all of the packages, and we're just interested in the package, you'll notice that when you make no granular, it goes from installed yes to installed no status. And now if I copy everything from granular into the source directory and then make package status, that changes to yes. So you have two ways that you can make a package. You can either copy everything from the file or just use make package status. Once you're happy that you've got all of the packages that you're interested in, you can then make your LAMMPS executable by make MPI or make whatever version of LAMMPS you want. If you go in the directory called make, there are a number of make files. Actually, in this case, there's only two. There's makefile MPI, which will let you have an executable that runs across multiple processors, or makefile.serial, which will let you have a single processor executable. Note, I usually install the multiprocessor one just because you can run on a single processor with the multiprocessor executable. You just need to specify I'm running a multiprocessor job on a single processor. But there's also machines, and depending on, there's a number of different machines, different supercomputers, different architectures, including say Macs, MPI for Macs, things like that. If you want to install LAMMPS with those, you will need to use those make files. The way you would do that, let us pretend that I'm a Mac user for a second. Instead of typing the make MPI that I showed you worked, you type make Mac MPI, and it will happily read whatever that file says. I'm not going to go through it because essentially it's going to try to compile a bunch of things. It's going to crash, and yeah, there's no point showing you a something crashing. Right. Let's make clean all to that. Good idea. And now I cannot remember whether I have CMake installed on this. So what I'm about to show you might not work. But there is a second way of compiling LAMMPS, and that is using CMake. Again, everything that I'm telling you is on the slides that I did for this presentation, and also in the LAMMPS user manual. But just to show you how it's done, it's on Archer. It's almost exactly the same way. The only change you need to make is you would need to also load CMake. Obviously, I don't have modules on my laptop, but that's the only difference for Archer. If you want to use CMake, first you want to make a build directory. Then you go into that directory, and then you. Hey, I've got CMake. This might actually work. Now I need to think what is my compiler. Not for the life of me. Is it just GCC? So it's unhappy because I've already got a version of LAMMPS installed. Let's get rid of that. Let's try again. And yeah, it's not happy because that's not my correct compilers, is it? So with that, I'm not going to be able to remember what my C++ compiler is on the fly. But very quickly, right, I'll look for it during the break, which will probably take now, if that's okay with everyone. And also during the break, I'll have running just the normal make MPI from here. So that's happening in the background. I think this is a good time to take a small 25-minute break. If anyone has any questions during the break, I will be here and happy to answer them. Sorry about the mild hiccup with the Archer going down unexpectedly. And after the break, I will be talking a bit more about some of the harder to make packages, things like Voronoi. I'll also be talking a bit about compiling for GPUs and briefly talking about how you can actually hack some of the LAMMPS code to maybe make force fields or fixes or computes that don't currently exist, where you can go to find help for that, and where you can go also to let the LAMMPS community know about this. I don't know if you guys noticed, but as part of the package list, a lot of packages had the prefix user underscore. Those are all packages that have been made by the user community or maintained by the user community, and there are some really good, really useful things happening there. With that, let's take a break, and I'll see you guys at past. And as I say, if you have any questions, please feel free to ask them. Okay. Very quickly, I wanted to say, so during the break, I had LAMMPS compiling in the background. And as you can see, it finished compilation with no errors and created a file called LMP-MPI. And if you now ls LMP-MPI, there's an executable, which is the LAMMPS executable with which I can now run simulations. I'm going to show something else in a sec, but first I wanted to go back to the CMake problems that I had. So over the break, I copied over everything into this directory called temp, which is just exactly the same as before. If I go and build, and the thing I got wrong is on my system, because I've got all my paths set out intrinsically in my system, I don't need to load modules or anything like that. I do not need to specify the CXX directory or what CXX compiler I'm using. It knows to use just the normal GCC compilers on my system. On Archer, that's not the case, and on Archer, you would want to use something that looks kind of like sorry, 1 second while I copy it over. You want to use something that looks kind of like that. So here you've got the DCMake CXX compilers, but here on my systems, I don't need to. And I can just run tmake. It creates all the CMake files, perfectly happily making everything. And once that's done, I just need to run make. And if I was doing this on Archer, instead of having run this command, I would have run this command with the DCMake CXX compiler equal to CC. And then, like on here, I would just have to run make, and it begins installing. The installation process is exactly as boringly long as on the other thing, except you get a lovely percentage sign, you know, like telling you that we're already 1% in. We're not going to sit through this compilation. But that was just to show you how to use CMake to compile LAMMPS. So having done that, let's go back to our source directory where we have our new executable called LMP-MPI. The reason it's called MPI is because I compiled the MPI version of, so the MPI version of LAMMPS. So When I did make, I said make MPI. If I'd said make Mac MPI, I would have ended up with an with a LAMMPS executable called LMP underscore MPI underscore LMP underscore Mac underscore MPI. That's just a naming convention. The next thing I wanted to talk to show very quickly, make package status. I'll need to find a it's not too difficult to do. Colloid. So you'll notice that at the moment I do not have the package colloid installed. If I want to install it, now that I've got my LAMMPS executable, if I want to install package colloid, I can make package colloid. Oh, it's uppercase. Is it uppercase? Oh, it's make yes colloid. Sorry, make yes colloid. Copy across all of the files from the colloid directory into here. And if I now type make MPI, instead of recompiling everything, it'll just recompile the added files, or it'll recompile the code, but just with the added files, which means that this second compilation will be much faster than the previous one. The previous one took about 10-15 minutes, and this one, I imagine, won't take much more than 1 or 2. So I'm not going to give it much longer. Oh, there we go. It's already done. So once you've got your initial executable compiled, you can keep adding packages as and when you want, and just recompile with whatever things you've added in, which is a great way to save time. Just thought I'd mention that. So going back very quickly to the slides. There we go. So I've shown you how to compile everything, and now I'm going to talk about the different packages. I've shown you how to add packages. Things like granular, I've shown you how you can include them by using the make yes package for make. I've not shown how you can do it in using CMake, but the way you do it using CMake is you add an option called -d and then the package name yes. So if I wanted to make the colloids package using CMake, I would need -d colloid all in uppercase equal to yes as part of the CMake command, and it would make it. Packages can be installed with make yes package name, uninstalled with make no package name if you're using make rather than CMake. And you do all of that in the source directory. I've shown you how to do that. The one thing I've not touched upon, which was hinted on, is there are some more difficult packages that one can build. One of which we mentioned was the Voronoi package. And I've never actually compiled the Voronoi package, so I might be getting this wrong, and there's at least one person in the chat who has compiled it before, so my apologies if I get this wrong. You can please feel free to let me know if I do. But I'm in the source directory. If I go into the Voronoi subdirectory, there's a README, and if you read the README, it will have instructions telling you if you want to make Voronoi, here's the things you need to do. It uses the Voro++ library. Voro++ library. Here's where you can download it. And then it'll describe what you need to do, the steps you need to undergo in order to install the Voronoi package. You follow those steps and it'll work. There's a couple of other packages that are also a bit more tricky, insofar as they need some other parts installed. If you go in the lib directory, so I'm in the top directory at the moment. If I were to go in the lib directory, there's a number of packages here, say netcdf, Cocos, Quip, even Voronoi. Voronoi, that's got the make file for installing, I imagine, Voro++. It tells you all of the instructions for how you can make LAMMPS, prepare the libraries in LAMMPS to work with the Voro++ package, usually you can just follow these instructions and they'll work. Sometimes, especially like definitely on Archer, sometimes there's some quirks to them, but to a very good first approximation, following the README usually works quite a lot of the time. So I just wanted to quickly touch on that. So that's how you compile LAMMPS. That's how you install packages. One of the packages you might have noticed, and I'll show you very quickly the shell again because I forgot I needed to show you that. I'm still in the lib. I'm not. I'm actually in the lib drawer now. I'm still in the lib, and one of the packages here is GPU. This is for GPU acceleration. Archer does not have GPUs, so I asked a friend of mine who uses GPUs to give me these installation instructions. He compiles on GPUs a lot and runs LAMMPS on GPUs as well. You can get a decent speed up on GPUs. The idea being that instead of having a handful of powerful processors, you can have a bucket load of not quite as powerful processors, but as long as you do your domain decomposition well, you can still get things to go a lot faster. GPUs for molecular dynamics are definitely looking more and more like the future, if not already the present sort of thing. A lot of research is going into really making GPUs either like making GPU performance incredibly fast, and there's definitely codes like say GROMAPS, which run specifically biomolecular molecular dynamics, which are incredibly efficient using GPUs. And LAMMPS itself also does have ways of getting a lot out of GPUs. So if you're ever wanting to run GPU simulations or compile LAMMPS to run on GPUs, here's the steps you need to do. So the things that are done on a GPU really well are things like long-range electrostatic interactions. And any peristyle it's also really good at. Anything like bonds, though, and dihedral angles, like because you've got less particles per processor, or you're running a larger system, I don't know. But yeah, you can sometimes get into communication issues, as in spend a lot of time communicating, but there's ways to make sure that doesn't happen. I'm pretty sure that for LAMMPS, you can only compile on GPUs if you've got an NVIDIA GPU and an NVIDIA CUDA driver, or NVIDIA CUDA drivers. And you need to compile the GPU library, which I just showed you, in whatever your LAMMPS directory is /lib. In the makefile, I'll actually show you this in shell. It's probably better than just having you guys read the slide while I read it out to you. So if you go into the GPU directory, there's a makefile. And there, I don't know, I mean, Linux system, makefile.linux, you can change the CUDA architecture. So here we've got loads of different architectures here. It's assuming that my architecture is SM30, which corresponds to a GTX 770. Depending on how good or how recent or old your GPU is, you can change the architecture to get the most out of your GPU. The way you do that is by, again, my friend has provided me a small list of which GPUs corresponds to which architecture as according to LAMMPS. And basically, if you've got a Titan XP, then you want an architecture SXT1, and you'd need a minimum CUDA 8. And once you've done that, you in the GPU directory, you make -j n -f makefile.linux.single, where n is the number of cores of machine core numbers. So if you've got a 16 processor machine, n would be 16. And that's how you compile on GPUs. I've not done this in a while, so I've not been able to test this, unfortunately. But again, I trust my source. So if you do try it out and find out it's wrong, please let me know so that I can update my slide. Now, I'd like to talk very briefly about changing source code in LAMMPS. And, this has all sort of been leading to this of, we've started by just looking at what a LAMMPS input file looks like. Then we looked at what the structure of LAMMPS looks like, which packages are where, how you can look at packages, how you can move packages around, how you can compile and things like that. And now it seems like the right time to start really just delving into those LAMMPS packages and seeing how you can alter LAMMPS, because it's actually surprisingly easy. Again, the rest of this, well, most of the rest of this will probably be in shell. I'm sorry. At least it's, shell on my computer, so you get pretty colors every so often. So, I'm in the source directory. And we said before that the files, if you ever want to make a package, you just copy them from whatever the package name is. Now, let's imagine for a second that LAMMPS doesn't have something you want to do. Let's say you want to run a simulation with a force field that's not currently in one of the available packages. There's a lot of packages. I think I showed you guys, there's, in the slides, I showed you very briefly, show you the slides again. In the slides, I showed you 2 slides back. This is the list of all of the LAMMPS packages and how to build them. And there are a ton of packages. There's a ton of packages. Including the standard packages and the user packages. Is that large enough? Let's make it bigger. Standard packages and user packages. And if you click on the standard packages, this is everything that's maintained by the people at Sandia who run LAMMPS. And you can look through the packages. It'll tell you there's an aspherical package, which is for aspherical particles. And there's a doc page. There's a doc page where you can find out how to use spherical particles. It tells you there are examples. So you know how I said there is an example directory? In that example directory, there's an example file called ellipse, which will let you test the aspherical particles. Do you need a library? No. And it goes through all of them. I've used probably maybe, I don't know, 1/5 of those max. Then on top of that, there are user packages, which are advertised on LAMMPS, which have been tested, well tested or tested well enough. They can be trusted. Sorry, I need to zoom out a bit because we're missing a bit of information towards the end. They can be trusted enough, but they are written entirely and maintained predominantly by the LAMMPS user community rather than people working at Sandia working specifically on LAMMPS. That's not to say that there's anything wrong with them. It's just to say it's not necessarily the same people doing things. There might be issues with integration or ones with integration rather than issues, but a lot of those are used a lot and they're all open source. So you can play around with them and check if you think they're correct and everything like that. Again, with these, I think I've maybe used 2 ever, but I know a couple of people who have used significantly more than just that. I got a question. The question is, are packages installed by default on Archer when you load up the module LAMMPS? Some packages are installed by default. I do not know off the top of my head what those would be and do not know where I could find that out. I'll try to find that out at the end of the let me see if I can just Google it, to be fair. I don't think I can find it immediately. Oh, there we go. So if you Google LAMMPS Archer, the list of optional packages installed is at the bottom, and as you can see, there are no user packages for 1, and for 2, there's also a number of non-user packages that are not installed. For instance, Voronoi isn't on there. So no, and this is the site where you can find this out. I will copy the site into the chat. I hope that answers the question. Yeah. Cool, cool. So with that, let's have a look at some actual LAMMPS script. So as I said in the first session, LAMMPS is entirely written in C++. So hopefully you're a bit familiar with C++, but basically for every so let's quickly look back at our day one input file, the input file that we were looking at on the first session last week. Just because there's actually, it'll make it slightly easier for me to explain these things. So last week we were using a pair style called LJ-cut. Now, when running LJ-cut, that means that somewhere there must be a file that takes that handles what that means for the LAMMPS executable. And in this directory, if we look through this directory, or if you spend time to look through the the 1,000 odd files in this directory, you will eventually find that there is a file called, or there's a series of files called pair underscore something, and actually that's quite nice. Right bang in the middle of the screen, you've got pair LJ-cut and pair LJ-cut.h. So those two files, which have the name pair LJ-cut, seem to correspond to the files we were using. And indeed they do, by the way. I mean, there's a number of different Lennard-Jones with a cutoff interactions in LAMMPS, but the specific ones we were using were LJ-cut with nothing else. So those two files correspond to the force field we were using in our simulation last week. There is a header file, there is a C++ file. In the header file, predominantly, it defines what the pair style is. So here you're saying the pair style can either be called with LJ/cut or uppercase P pair, uppercase L, uppercase J, uppercase C cut. Those are the two ways that you can call this specific command, whatever's listed in this header file and in the associated C++. When you write your LAMMPS input script, you can use either of those two to call this file. And both of those will return without error. Then it tells you, here's how we're defining this. We need this other header file, which is part of LAMMPS, and then it tells you all the different libraries that you need for, like, it tells you all of the different sections that you'll have in the C++ file, as well as telling you all of the protected variables for this function. If you then look at the C++ file, you actually get the code. And just to show you that this is the code, here you're calculating R6 inverse, which is 1 over R to the 6, which is equal to R2 inverse, so 1 over R squared times 1 over R squared times 1 over R squared. And then you can get the Lennard-Jones force by multiplying this. You will also somewhere calculate R12, presumably, or do you just do R6 squared? Ah, there we go, yeah. The Lennard-Jones force is equal to 1 over R to the 6 times the first part of the Lennard-Jones times 1 over R to the 6. So we've got a 1 over R to the 6 times the 1 over R to the 6 of us, the R to the minus 12 term, and then the other term is just the R to the minus 6 term. There's a lot of other things in this code. Here it tells you how to calculate the x Y and Z force every time step. Here it tells you if you've got Newton pairs and things like that. This is just C++ code. Well, not just, but yeah, it's C++ code. But let's say, for instance, that you've got this, well, you know, instead of wanting to do difference potential, you wanted to do, for whatever reason, you just wanted to do a pure r to the minus 12 repulsion without any attraction afterwards. As far as I'm aware, there's not currently any things that do that in LAMMPS. How would you go about it? Well, usually the first step that you do is you try to look through all the pair styles that already exist in LAMMPS and try to find something which is slightly similar to what you're trying to do. In this case, we want just 1 over r to the 12. We don't want the minus 1 over r to the 6. So we can use this, this bit of code which has something over r to the 12 minus something over r to the 6. Just get rid of the r to the 6 bit. So the thing we can do is take this command, and let's copy it across and call it plus and dot h. Yeah, that's all right. Then we'll be looking at pair equal. I did it in uppercase because usually uppercases, every C++ and header file is lowercase, so this is just an easier way for me to spot, this is something that I've messed with when it comes to needing to delete it for whatever reasons. What I'm about to do as well is I'm going to try to, you know, make a fake pair style in LAMMPS live. This might go horribly wrong. I apologize if it does, but, you know, we'll see. So first off, as I said, this is how LAMMPS would call this pair style. Unfortunately, there's already a pair style which is called with LJ cut and pair LJ cut. So if we were to try to make LAMMPS again, it would very quickly go, hang on, you've already called this, error, crash out. Hopefully quickly. Oh wait, no, it's just remaking everything, isn't it? Because yeah, sorry, we won't be able to test that then. Oh no, what way of doing it? Sorry, I am making LAMMPS install itself in the background, and I will show you what you can alter, here while making LAMMPS compile in the background. So I'm going to move. So I've moved both of my pair examples into this file, which means that now when I make LAMMPS in the background, or compile LAMMPS in the background, it won't use those files, and that way hopefully we can do tests when this is all done. My apologies for this. This is because I showed you how to do the cmake command, and I needed to uncompile everything for the cmake command. Oh, I tell a lie, apparently it is happy to go. Okay. If I make MPI with the examples, it won't be happy. It would be nice of it to not be happy quickly, though. There we go, we have an error. And you'll notice that the make MPI finishes with error 2 and tells you the recipe for target MPI failed. That tells you I wasn't able to do the thing because there was an error. If you go up, pair examples here, it says this here tells you where all of the errors arise. And if you look through here, it says right there, in pair.example.cpp, there is something that's already defined elsewhere. Namely, pair LJ cut is already defined somewhere else. So these two lines are the ones that are of interest. Sorry for the highlights. It's not the best, I know, but it's the best way to bring out the text of interest. It's telling you that there's in parallj_cut.cpp, there's something called parallj_cut, and now also in parexample, there's also something called parallj_cut. What's going on? You're defining the same thing twice. What should I do? Fine. Our first step is we need to rename these. In keeping with my amazing naming convention, they're just going to be renamed. For example, here I don't even need the LJ slash. I could just have, actually I'll have that as LJ example, probably better because it's not quite like, yeah. Then here you'll need to change that because otherwise I'll try to define the same thing. Include pair, yep, that's fine. Namespace lamps. And now we're just quite literally finding all of the places where it says LJ cut and changing them to example. This is the not very exciting bit of the. And now if we look, there is no LJ cut left anywhere, so we've gotten rid of all of the LJ cuts. We're done with the header file, hopefully. We can now move on to the C++ file. And in the C++ file, first of all, you'll notice that the very first file that you need to include is the header for LJ cut. But that doesn't exist anymore, or rather, this is the one that we want to make anymore. We want pair example, so we need to rename that. Then, just like before, probably the first step we want to do is find all mentions of LJ cut. And did we have it as an example? I think we have an example. Change those to example and all uppercase because, yeah. So go through the directory, find all of the LJ cuts. There's a fair few of them. I can't remember if LJ cut is drastically large or not. So change those, change those. Yeah, that is a faster way of doing it. Let's just change all. Sorry, 1 second. There we go. Boom. Find all occurrences of LJ cut and sort them to example. There we go. And if we look for LJ cut, there's no more LJ cuts. Thank you very much. So having done, we now have two files that will compile. They'll do exactly the same thing as sorry, they'll do exactly the same thing as what LJcut does at the moment because we've not changed any code. We've just said that there's now a new force. There's now a new force field called example, which is going to do exactly the same thing as a LJ cut. Is it not happening? That one looks like that's wrong. Maybe I'll find. As I said, there is a definite likelihood that I won't be able to show you right off the fly how to do this, but should be fine. Why aren't you happy? Sorry. Obviously, still going to fail because I've not changed anything in the file. Well, that's your first issue. It's probably just that I've left something in that I shouldn't have. So the risk of doing this is that you can end up with a lot of errors. That's why it's pair underscore. For example, I think that's it. Sorry about this. So I think that's what it is. So I called it here pair LJ example as opposed to pair example, whereas in the C++ file, I called them all pair example. Also, I forgot to rename that. Boom, let's rename that and then do again the command. I want example to LJ example. Boom. Here we go, and now that's substituted, so everything says LJ example, and now hopefully, when I run make MPI, at the moment, everything is named the same way, and hopefully we won't get a bunch of errors. Oh. We get one error, because, again, I'm being a bit of an idiot. There, plus. That file is called pair example, not LJ example. There. And now it's happily compiling, and what it is compiling, however, is two versions of exactly the same information in pair LJ cut, because at the moment I have not altered anything other than the links, other than the object names. So now we have a force field called pair example, which does exactly the same as pair LJ example, and now we can start to alter it to do what we want. All alterations for that sort of thing will be in the C++ script. And mainly what we're trying to do is we want to get rid of all mentions of like everything which is just r to the 6. Everything that's r to the 12 we want to keep, everything that's r to the 6 we don't want to keep. So in this case here we have r to the 6 times something times 1 over r to the 6, and then minus something times 1 over r to the 6. Sorry, let me restart. Here in this line, we've got a line which says take the r to the 6 inverse, so 1 over r to the 6, multiply by something times 1 over r to the 6, which gives us our 1 over r to the 12 term, and then take away something by itself, but because it's in brackets, that would get multiplied by 1 over r to the 6 to give us our 1 over r to the 6 term. We are trying to get rid of the 1 over r to the 6 term, so we can just simply delete in this case. If we wanted to do something more fancy, we could totally do something more fancy, like have 1 over r to the 3 or anything like that. But in this case, because I just want to show an example of what it looks like, I will just simply delete it. And likewise here, we've got an r6 inverse times r6 inverse minus something which is not times r6 inverse. So we get rid of that bit. And there's a couple of places where this happens. First of all, in the compute part, this is where the forces are computed. You'll want to get rid of that definitely. There's also the compute inner is basically because this is a pairwise interaction. The compute inner is for the inner loops rather. Yeah. So here we'll need to change it as well, and you'll notice here we've got again our r to the 6 inverse times r to the 6 inverse minus something that's not times r to the 6 inverse, so we get rid of that. One here, or are we? Oh, here it's just computing the forces rather than the energies. So this is all fine. Here we'll need to get rid of another one. Various force fields are more or less complex to do this with. I chose the Lennard-Jones cutoff one because apart from completely messing up my names and getting a bunch of errors at one point, this is really a very simple force field, which I know call, so I feel, semi-confident we might get something okay out of this. Again, there's much more efficient ways of doing all of this than the way I'm doing it now. But this also gives me a chance to talk about things. So for instance, every pair style has an allocate part. And the allocate is where you can define all of the inputs that you're getting. So if you remember with our pair style, let's have a look at it. With our pair style, we needed to define pair coefficients. Pair coefficients said that an atom of, in this case, an atom of type 1 interacting with an atom of type 1 would have an epsilon of 1 and a sigma of 1. All of this sort of thing is defined in the allocate part of the code. And you'll see that it'll say, well, okay, does it have a cutoff defined? Does it have an epsilon defined? Does it have a sigma defined? Does it have first, second, third, or fourth term defined? Any offset defined? All of you set them. If you wanted to input more things, you need to add a line and allocate. Settings tells you how many arguments you should expect. And so here it's saying, it's telling you, well, if you don't have this number of arguments in your pair style, send back, well, this is a wrong command. If you wanted more inputs, you would need to change what those numbers are. Coefficients, likewise, this is, so in settings, this is telling you if you have more than one setting, which is the cutoff, the truncation cutoff for the Lennard-Jones force, when you define pair style LJ cut, if you don't have one number that tells you the truncation distance, the cutoff distance, send back an error. Then for the coefficients, it's telling you, well, okay, whenever you use, whenever you name pairs, whenever you say type 1 is interacting with type 1, if you don't have In this case, if you don't have the number of arguments here, so in this case, arguments less than 4, arguments more than 5, then send back in, and then it tells you here are the things you should expect. So if you wanted an extra argument for your pair style, you'd need to add it here. Init style is for when you're initializing everything. And then init1 is for a single one-off calculation. So here should be the last place where we care about deleting anything, and we just need to delete these 2 lines. Get rid of this. We're also very close to this file. And there we go. Is that us done? That's us pretty done. That can go away. Go away. I can't remember. Maybe it shouldn't have. Oh, probably won't crash because that's hardly ever used. Be more careful when you change your own codes than I am. This is really just to show you guys, like I'm trying to juggle both showing you guys what the LAMMPS code looks like while also trying to change script. Write restart tells you how you want to write a restart file. Read restart tells you how you can read a restart file. So a restart file I didn't really talk about. One of the options that LAMMPS gives you is to, after a simulation, write a binary file, which is all of your positions, velocities, as well as certain things like the pressure of the system, how the simulation box looks like, things like that, so that you can use your restart file to just restart from that point. And write and read restart tells you how to handle that. More on restart, and then write data is for any dump file or any data file. If you want to just make a data file that's then put in, you can write a data file. And the single is the last bit I need to removing. That goes away. That goes away. And that's us done. So now we've got a different pair style, which should hopefully which will hopefully just have the repulsive interaction, i.e. 1 over r to the 12 interaction of the Lennard-Jones interaction. I've changed the file. LAMMPS now knows, oh, this file's changed since the last time I've compiled with it. I will just recompile that file. Or rather, the compilers are aware of this. So now we've got a LAMMPS executable, and we will try to see if what I just did works. Slash LJ to here, and then we will. So at the moment, I would like to first run a version of this, which still uses the LJ cutoff interactions, just so we've got something to compare against. C, LMP, MPI, in.lj. This will be a bit longer than an Archer because, well, first of all, I'm using 4 processors rather than 24, and so this is happily running, doing its thing in the background. I think I showed you guys before the outputs, but here specifically, the outputs likely to change will be potential energy. So the 4th column is what we'll be interested in seeing whether that changes. Whereas at the moment, we've got a potential energy which is negative because there is a potential energy where particles can be happy. There's a minimum in the potential energy for a Lennard-Jones system. For our example system, because we've got rid of that attractive interaction, the potential energy should always be positive. That's the idea. So now, let's change our pair style from LJ cut to LJ sample. And if we run that again, there we are. If you look at the fourth column, the entire of the fourth column is now positive at around +2, whereas in the previous run it was a -4. So this is not a proof that we have successfully done this, but it looks like it's outputting the right thing, at least to a first approximation. So that is really how, that is exactly how you would go about changing a force style, a pair style even, sorry. So there, it's happily running. You get the final output, and that's that. I'm not going to go through all of the different files that you can change, but every compute is here. So, for instance, all of the RDF computes are here. Velocity autocorrelation function computes are here. All of those files are already available. Usually the easiest way to start developing your own code is to take pre-existing code, changing it a bit, and using that as a baseline from which to build. So I'm getting a question. And I'm sharing the wrong thing. Sorry, I will share the right screen and then I will answer the question. That's the screen I want to share. And the question. Is there any way not to see outputs easily for larger files and directly see the saved outputs once everything is complete? Yes, so the reason you saw the outputs is because at the moment I'm running on my home system. If you were to run this on Archer, you would be submitting your job to a job queue, and everything would run on the queue. You'd only get the output once it's finished. To not print everything to screen, you would be able to, for instance, use it. So I'll show that real quick. And you can also run in background. So I will show really quickly how to do that if you like. Is it this one or this one? Let's go with this one. That's cool. So very quickly. LAMMPS in.lj. At the moment, it's outputting to screen. I can. It's legible. It's not actually that much better. So at the moment, it's just running and everything gets output to screen. I can, however, use a caret, send it to output. It's now still running, but when I kill this, you'll notice there's now a file called output, and if I look at output, it has, well, if I let the job finish, everything that was printed to screen would have ended up in output, and then the last thing I can do is run in background by using ampersand at the end. And if I do htop, here we go. There's a process called LMP-MPI, which is currently running in the background. And when that's done, because I launched it on, well, because I was silly and launched it on only one processor, that'll probably be done in about 2 minutes. But basically, it's running in the background, it's outputting to the output file every so often, and when that's done, that's done. I hope that helps. So back to the slides. We've done compiling packages, we've done that, and I've mentioned the ways that you can alter source code in LAMMPS. So with that, we've basically covered everything I wanted to cover. So I'd like to briefly say a couple of things. The first thing I'd like to say is next week from 2 till 4:30, This slot will be for an examples class. As I said at the start of this presentation, I'm still currently writing the examples that I've got, one which is up already, one which will be up by the end of the day, and another at least two coming. If you want to do them over the week, if you've got time, please feel free to. Otherwise, they should all be doable in the 2.5-hour session. And definitely in the last half hour, I'll show you all of the answers to to at least some, if not most, of the problems in it. You're more than welcome to come to that example session if you think it'll be useful for you. If you feel that actually everything that I've said here is stuff you already knew, or that you're definitely experienced enough in LAMMPS that you don't need the example session, that's absolutely fine. It is in no way mandatory. At the example session, one of the questions I just got is, can we bring our own material to the our own material systems as examples? You're welcome to bring the examples you're interested in to the example session, and I'm happy to answer questions from people about their systems. I'm not saying that I'll be able to answer all of them, but I'll certainly try to answer or help as much as I can. So there, I will be here for a back and forth for about 2 hours and answer as many questions as I can, be they about this course or about your systems. And then for the final half hour, I'll go through some of the solutions to most of the examples. But this is not mandatory, compulsory, or anything like that. So with that in mind, I also wanted to flag up, I'm also aware that some people need certificates of attendance to show that they've been to a certain number of courses. The way we do these in EPCC training is we set an exercise for you all to do in your own time, anytime after now, basically. And the exercise is something for you guys to do just to show that you've attended these courses and you've listened to these courses. And based on the answers you submit, when you submit your answers, we will then send you, check that the answer is correct, and then send you a certificate of attendance for your course in case you need that. In this case, the exercise I've set is the code we used last week in .lj. We were only running canonical ensemble, so we had fixed the volume and temperature of our simulation box. However, a lot of physical systems tend to be more isobaric isothermal ensembles, i.e. with fixed pressure and volume, pressure and temperature rather than fixed temperature and volume. So I'd like you to alter that code, and if you could send the log.lamps file that is produced by a system that runs an isobaric isothermal ensemble with fixed pressure to training@epcc.ed.ac.uk, we will use that to send back your certificate of attendance should you need one. Last, I want to again mention, I should have mentioned this before, that's on me. If you're wanting to modify and extend and change your own code of LAMPS, these two links are super helpful. The developer's manual sort of tells you exactly how everything is laid out, so that if you want to change a fix, you can read that and it'll tell you, well, when we look for a fix, here's the first thing we're looking for, here's the second thing we're looking for. It's very wordy, which is not necessarily a bad thing when you need something to fit exactly with the previous structure of LAMPS. And for just modifications and extensions, there's the link as well. And with that, I wanted to thank you all for sticking it out for these two sessions. I hope I'll see some of you next week as well. And I especially wanted to thank Claire for, frankly, she does everything behind the scene. Like, the only reason this is here now is because of the amount of work that Claire's been doing. Juan as well, who I should really name on slides, who is the organizer for all of the training. Rui, who is the person that I asked for GPU information, and Ranga and Yang, who really helped me for all of the processing software from day one. If there are any questions, I'm happy to answer them between now and whenever there are no more questions. Otherwise, I hope you all have a good day, and I hope you all enjoyed the course. And hopefully see you next week.